Uh, okay. Uh, okay. Here. We're ready whenever you guys are. Should we start now?
Yep, go ahead.
Okay. Hello everyone, we're Team Flexisense. We're an interdepartmental team from electrical engineering, computer engineering, and computer science and bioengineering. Our advisors are Dr. James Weimer, Dr. Nathan Lazarus, and Dr. Clay Jones. Dr. Jones is a pediatric rheumatologist at Walter Reed National Military Medical Center. Most of her patients are small babies, but they suffer from irregular and unpredictable fever. A continuous temperature profile is a key to her diagnosis. Patients' temperatures need to be checked every single hour. When these patients are staying at the hospital, they have to be waken up by nurses for these temperature measurements. And we all know it is really hard for crying babies to go back to sleep. Even when these patients are discharged, their parents will have to do the same thing, but this is nearly impossible for most parents because they have to go to work or sleep at night. This issue not only troubles Dr. Jones and other pediatricians, but also is pertinent to every doctor and patient that needs vital measurements. Here's why. Patients' vital signs, including temperature, blood pressure, and heart rate measurements, need to be taken by nurses every day. However, this process currently is very inefficient in hospitals. We can see in these pictures, nurses need to carry these bulky devices around and manually log the data into the system. In addition, nurses on average spend 35.5% of their time checking and logging patients' vital data. But the average nurse-to-patient ratio is only 1 to 4.89. What if we could solve all these problems with a simple, soft-conformal biosensor? So with the guidance from Dr. Lazarus of the US Army Research Lab, we created Flexisense. Flexisense is a flexible, wirelessly rechargeable biosensor platform that automates patient vital monitoring. Even for this ongoing COVID-19 pandemic, doctors and nurses can greatly benefit from this device. Medical staff can reduce unnecessary contact with individual patients. Moreover, this device can be easily manufactured and distributed in large quantity to alleviate the issue of nurse shortage.
Sorry, I just muted myself. Now let's go to the most exciting part, our technology and device. Here are the schematics of our device. The PCB charges the onboard battery wirelessly from the power unit, which should be placed under the bed sheet. So when patients lay on the bed, the device is charged on their body. The sensor takes measurement at a regular interval, which can be set on the user's end. Then the data is uploaded to the cloud through Bluetooth. The data needs to be encrypted as it contains medical information. The nurses and caregivers can view the data on their phone or desktop and log into patient's EMR. Overall, the device automates the entire vital monitoring process to provide continuous care. And next one. Our prototype weighs less than 50 grams and has a dimension of 7 centimeters times 5 centimeters times 1.5 millimeters thickness. The charging coil is the largest component. It's definitely possible to shrink down the size of PCB and battery, or use a smaller coil with less turns and smaller diameters. Without charging, the battery could last for at least 2 days, and recharge takes less than 5 hours. Wireless charging can be done over 1 centimeter's distance, which is the thickness of bedsheet and cloth, transmitting power at 100 milliwatts. Bluetooth range is over 3 meters, so a receiver can be placed next to the bed like a smartphone. The temperature sensor we're using has an accuracy of 0.05 degrees Celsius, which was recommended by the advisor. Looking at the chart on the right, we're comparing to the traditional vital monitors. Flexisense satisfies all customer needs. The device has 4 main components: flexible electronics, wireless charging unit, PCB, and microcontroller, and user interface. We're going to briefly talk about them here, but the demo video will go into more details. One of the most important features of the device is that it's flexible, as you can see in the upper right picture. So it's very comfortable to wear. The power receiving coil is fabricated with liquid metal injected in silicone tubing. Liquid metal is gallium and indium alloy. It's non-toxic and stays liquid at room temperature. The PCB is connected to the coil with a short copper wire.
We designed the wireless power system to optimize for efficiency at 1 coil diameter distance. By choosing a resonance frequency of 1.5 MHz, off-the-shelf power electronics can be used to reduce cost, and efficiency is increased for greater range, up to 4 centimeters. In the picture, you can see a simple testing circuit with copper coils as transmitter and receiver. The LED is lit up, indicating that power is received. When we switch out the copper coil for the liquid metal coil in the demo video, resistivity of the coil increases by 10 times, so the distance drops to 2 centimeters.
The picture you see on the right is our current prototype board. On the top right, it has the NF Bluetooth module, which is a popular chip used in many DIY Bluetooth projects. A digital temperature sensor is placed at the back of the chip for close skin contact for better accuracy. The board is also connected to a LiPo battery with the wireless charging circuit. The chip was designed 2 layers instead of 4 layers to reduce the manufacturing cost, and right now it is designed to be 3.5 by 4 centimeters. Over Bluetooth, the temperature data measured will be sent from the chip to the cell phone application, and from there, the data will be uploaded to a Firebase database for transmission to the hospital system and to the doctors. From the app, the patient can also enter their symptoms, their medication doses, and review all the data real time at their convenience. Since all of this is sensitive health data, it has to be stored in an encrypted form on the server. For this, we can integrate to an existing hospital system or use standard libraries for file encryption for protection.
Important standards are the FCC CFR, which limits what open bands we can use. The FDA Class 1 medical device means that our device is non-invasive and only for monitoring purpose. We have considered a few alternative designs along the way. We try to use the Qi standard for wireless charging because chargers are commercially available, but 15 watts of power to charge your phone would turn Flexisense into an induction cooker and cook the patient's skin. We also considered alternative form factors, such as a patch to glue onto the patient's skin using 3M skin glue. We decided that a wristband will minimize the skin discomfort. Unfortunately, we did not finish manufacturing the wristband before school closes.
Now the less exciting, but also important part. Based on our unit cost, we plan to price our device at $100 per unit, which gives us around 21% margin. Our main market will be the hospitals, but there are also opportunities to expand beyond the hospitals, such as home care or military use or physical therapy. And last but not the least, we'd like to thank all of our advisors and the senior design team for their help and support. And thank you. That's our presentation.
Thank you.
Thank you guys. Now, would you think it'll be easier for you to share the video in the chat or to play on your screen?
Share the video in the chat. Would be
Okay,
easier.
let's go ahead and do that.
The video can be directly played on the dev post page.